Welcome back to the video lecture. Now we'll be discussing about the edge detection. Edge pixels are the pixels at which the intensity of an image changes abruptly, and edges are the set of these connected edge pixels. And edge detectors are the local image processing methods which are designed to detect the edge pixels. And the basic goal of this detection of edge detection is to identify the sudden changes or the discontinuities in an image. And intuitively we can say that most of the semantic and shape information from the image can be encoded in edges, and it's more compact than the pixels. And here is an example of edge. We can see here we have got the image on the top. The top figure shows the original image, and the detected edges of this image of this object can be seen below. It is just a very basic example, and we will see in detail how we can detect these edges. And there are variety of factors that causes the edges. Like one is the surface normal discontinuity. When the surface gets discontinued at some point, that also gives edges. Another one is the depth of the object. Another one is the surface color discontinuity. When color changes abruptly, also it gives it generates the edge. And another one is the illumination. It's caused by the light of light. This discontinuity is also caused by the light. And now we'll discuss about the various model of the edge, and we can classify the edges according to their intensity profile. First, we will see the step edge. This step edge involves a transition between two intensity levels, which occurs ideally over the distance of 1 pixel. Here we can see it just occurs along the 1 pixel, and these edges occur in images generated by the computer for the use like these are used for the use such as solid modeling or the animation. And the clean ideal edges can occur over the distance of 1 pixel, as I have said before, provided that no additional processing is used to make them look. So these are occurred just within the interval of 1 pixel, and when no additional process are performed. And this kind of step edges is frequently used to make them look like a real, like here you can see. And another example is the ramp model. And in practice digital images have edges that are blurred and noisy, and in such situations edges are more closely modeled as having intensity ramp profile. And here it no longer contains the single pixel, and instead of uh, uh, one point content in the ramp, an edge segment would be a set of such points that are connected. Like it consists of a set of points that are connected. So this type of edge consists of the set of pixels. And third type of edge is so-called the roof edge. Here we can see here, and these are the models of lines through a region with the width of edge being determined by the thickness or the sharpness of the line. And when the width or the base is 1 pixel wide, it looks as a 1 pixel line returning through a region in an image. And this edge arises, for example, in a range imaging, when both objects are close to the sensor than the background. And here we can see that we have got this is the image of pipe, and what we can see here is the pipe appears more closer to the sensor than its background. And if we see the intensity profile, it looks like this, like it goes up. In case of roof model, it goes up and it comes down again. And here the pipe appears brighter, and thus it creates an edge. As shown in the figure, we can see this is the edge, that is edge profile, that is uh, created by this image of pipe. And these are the basic models of the edge. And if we look at the close-up of image, this is the, here we have an image, and if we look close up, like if we take the sub image from this whole image and make more close-up, then we can see this intensity profile which changes, the intensity changes abruptly, and this creates some sort of step edges. And here another part of the image, and like we can see here, it consists of lots of area that consists of edges. And this is just the simple definition of edge. Now we'll go for the detection of edge. Like we saw so far, like different edge models. Now we'll be discussing about the different techniques used to detect the edges. As we know, edges are generated by the average abrupt changes in intensity of pixels. So if we detect these changes, and we can detect edges, and we have already discussed in our previous video that local changes in intensity can be detected by using derivatives. So we also discussed about the first order and the second order derivatives and its application in our previous video. Here we will see, we'll again discuss about the first derivative. And here we have got very simple example. Here is the image. This image consists of a line, or this consists of a line, and this line is the here we, in this line we will take the intensity along this line, which is marked here with the red line. And in the next figure we can see here, this figure shows the intensity profile or intensity value along this horizontal line. And here it starts out high, it starts out with the high and then comes down smoothly and goes back to the high again. And now if we apply the derivative to this function, we will get the result like this. We can see the result of this is the result of the first derivative when applied to this intensity function, and we will get the result where we see the two extremas, and these two extremas correspond to the changes in the intensity in the horizontal line. We see here the two extremas, this one and this one, and this corresponds to the edges, and or these extremas are occurred mainly because of the edges, or where the intensity profile changes abruptly. And so finding the edge is going to be it's going to be have something to do with finding the peaks in the derivatives. Here if we find the peaks of the derivative, then we can find the edges. So we use differential operator to get the derivative, or when we apply it to the image, it returns some derivatives. So we model the operators as a mask or the kernel that compute the image gradient. So and the image gradient is nothing but the vector made up of these derivatives. And next we threshold this gradient function to select the edge pixels. And in this way we will detect the edge. And next Now let us see in more detail about the image gradient. Well, in multivariate calculus, we have a function of more than one variables where we can take the partial derivatives, which is derivative in the x direction or derivative in y direction. Like here we have got we take image, so we take which is the image is two-dimensional function, so we take only x and y. We consider the derivative along the x direction and the y direction. And we can see here the images. Like here we have got the different images, and in first image we can see the partial derivative along the x direction, and here we can see the changes occur only in the x direction. This is the first figure where we see the changes occur only in the x direction, and we don't consider the derivative along the y direction. In the second figure, we see the derivative along the y direction. Here also we take the partial derivative along the y direction, and here change occur only in the y direction. However, the image changes occur in x direction as well as in the y direction. So the gradient consists of the partial derivative along the x direction as well as the y directions. This is the gradient of image, which consists of the partial derivative along the x direction as well as in the y direction, and this is the gradient operator, which consists of this derivative along x direction and the y direction, and it comes with the magnitude. And we can take the magnitude of this gradient, and this magnitude of gradient is nothing but the we take the square root of sum of square of these derivatives, and this square these derivatives can be written as mx along mx and my. That gives the magnitude of the gradient along x-axis and along y-axis, and we can also get the direction of this gradient, which gives the inverse tan of the ratio of magnitude of derivative along the y-axis and magnitude of the derivative along the x-axis. And to save the computation, the magnitude of the gradient is usually approximated by the modulus of magnitude of derivative along x-axis and the modulus of derivative along the y-axis. And here is the example. Here we have the image, and we take the derivative along the x-axis and derivative along the y-axis. In case of derivative along the x-axis, this figure shows the derivative along the x-axis. Here we can see only the vertical strips, because it changes. The changes are we take the derivative along the x-axis, so it detects the changes only in the along the x direction, which is same in case of y derivative along the y-axis. And when we take both, then we get this image. This is the gradient of the image when we take both the derivative along the x-axis and derivative along the y-axis, and take the sum square root of sum of the squares of the derivatives. We get this image, and this image gives us the edge information of the whole image. And let's talk about the discrete gradient. So far we have discussed, like here we take the derivative along the x-axis, like we take two neighboring pixels, and here in this case, in this particular operator, this operator operates on the current pixel and its previous pixel, or its preceding pixel. But there is no special reason, like then the question arises, like why we are taking only the previous one as well. We can take the next one as well. So here it doesn't consider all the possible gradient of all the possible pixels. So the it is not the perfect one. So in order to consider the previous one and the next one, we take this operator. This operator here, it considers the previous one and the uh, next pixel, and it is obtained by this operation. Here what we do is we take the previous one. In this case we take the, here we can see that it takes the previous pixel, and the and this operator, this marks considers the next one. And if we take these two, if we average these two, then we will get this operator, and it will come up with this mask or this operator. And so this operator gives us the average of the left and the right derivative. So in this case only the left, it was considering the backward difference or backward derivative, it was, and it is considering, here we can see it considers the forward difference and it considers the backward difference. And when we take all of these two and take the average of these two, we will get the average of the left derivative and the right derivative. So it will end up with this operator, which gives more better result than the only the left one. Okay, now let's go to the another operator, and now we'll discuss about the Sobol operator, and this is the most widely used Sobol operator. And the idea here is, if we are taking the derivative, we assume that the image is locally smooth, that is they change similarly within that region. So in our previous example, what we did was we just take the, like here in this case we will take only the left one and the right one. We consider only the pixel in my left and the right. But in case of Sobol, instead of considering only the left and right, we are going to compute the derivative at the pixels that I won't look only on the left or right, but also look above me and below. And then we normalize it by dividing by the 8. Here what we do is we normalize, we consider the pixel above me and above and below me, and we normalize it by dividing by 8. And this is what we get after this. Like it also have the gradient along the x direction, or the derivative along x direction, and this gives the gradient along the x direction, and we get the gradient along the y direction. And what we do is we get the magnitude as we obtained before, and we also have the angle of this gradient. And there are some well-known gradient marks like Sobol, Prewitt and Roberts. In case of Sobol, what we notice here is, in case of Sobol, this gives importance to the center pixel, and in case of Prewitt, it considers all the pixels equally, like it doesn't give preference to any specific pixel. And in case of Robot, it considers the diagonal pixels. So these are the different types of the operators or the gradient marks used to detect the edges. And here we have original image. Here this is the original image, and this is the gradient magnitude that we obtained, and this is the thresholded gradient. After we perform the thresholding, we get this the gradient magnitude, and this is obtained for the Sobol operator. And next and this is for the Sobol order. And next we'll be discussing about the effect of noise on the edge. Now let's take the example of real world problem. Here we have a function fx. Here intensity is the function of x, and if I take the gradient of this function by just doing say a right difference, then what I will do is apply my derivative operator, and I'll get this result. So after seeing this plot, one might ask, where is the edge? Like we cannot find the edge in this figure, and we can see that edge in the function. However, the plot of derivative shows only mesh, so it's hard to tell about the edge. So, and the problem of course is that we have added the noise. So, and the noise has caused us to have this positive and negative derivative all over the place. So let's look a little bit more about the effect of noise and some of our derivatives and what we might do about them. Here is an image. Again, this is the image segment of zebra strips, and here we have a gradient image as well. And what we can start to see is that we add noise to the image, and the gradient starts to fall apart. Like we can see here, we have the image is corresponding gradient, and we increase the noise and see its corresponding response to the gradient of the image. And here we are starting to see that we had this little bit of Gaussian noise, and now it's turning into this big salt and pepper noise. And it feels like with the salt and pepper noise, these large spikes are happening within the derivative. We can see here large spikes in this derivative or in this gradient image, and so we have to handle that noise somehow. And the question arises, how we will handle this noise? And the answer is easy. We will filter or we smooth the noise to get rid of it. So again, here is a function fx. So now here's a function, and what we do is we smooth this function with this kernel z, and this is the with the sigma 50 we apply a smoothing function, this kernel z, and we are just gonna smooth it. And so we when we smooth it, we get this g convolved with f, and this is the convolution. This is the result after the convolution. Here we convolved g with f, and now we get nice smooth and after we do the differentiation, we get this nice smooth function, and this is our edge, and where we get the nice smooth peak. So here is the edge. We can easily find out the edge. So the edge is going to be at this peak right here, and here we get the peak here. So basically, in order to find our edge, we are going to have to apply smooth gradients. So how? And so somehow, and look the some peaks. And since the differentiation is convolution, here we can see, since differentiation is convolution and convolution is associative, the derivative of g convolved with f is same as the f convolved with the derivative of g. Here we can see here we have got this derivative of f convolved with g is same as f convolved with derivative of g, since we have already stated that this is the differentiation differentiation is convolution and convolution is associative. We have discussed in our previous lectures. So this will save us our operations. So what I do is we'll take the g and take the derivative of g. Here we'll take the derivative of g, and when we apply that function directly to f, and we apply this to f, and we get out the same value that we got last time, and which has to be because of the associative property and linear operations and derivatives and filtering these linear operators. And that also saves the operations because we can just take the filter and apply it, and no more derivative have to be done. Like we can just take this filter, we can take this filter directly and then convolve it with this function. We'll get this peak. So here we have got, and the last question one is we have this nice peak and we have to find maximum of that derivative. Here we have got this nice peak and we have to find the derivative of this. And how do we find the maxima? And we take more derivative. Suppose if we take more derivative, now instead of taking single derivative, we're gonna take second derivative, and before h was just a Gaussian. If we take the derivative of Gaussian, now if we take the second derivative of Gaussian operator, and we get this inverted Mexican hat, we can, like, if we take the second derivative of this Gaussian, we get this inverted Mexican hat. And now if we convolve this kernel with our function fx, we get this nice zero crossing, like we get this nice zero crossing, and with this here we get the strong slope, and this is what corresponds to our edge and this zero crossing. And in this idea of strong slope zero crossing, we don't have to find the general maxima, and we just have to find any place where the value of 0 and that nearby has a strong gradient. Like we just have to find, if we find this zero crossing point, we don't need to find the maxima, and and we obtain this by using the second derivative of Gaussian operator. So far we have studied about the derivative of Gaussian in one direction and its effect on the suppression of noise and taking the edges or so far we have discussed about the Gaussian. So far we have discussed about the derivative of Gaussian in one direction. In gradient, we take the derivative in x direction and derivative in y direction. So when doing the same trick of taking the derivative of our filter, in what direction are we taking the derivative of Gaussian that determines the derivative of Gaussian? So let us suppose we want to take derivative in x direction, and this little h here we have the expression here, this little h in this equation means to imply is that that's a little filter, and that just takes our derivative in x direction. This will take the derivative in x direction, and maybe it's a Sobol operator, or maybe it's some other operator, but it's a small filter taking a derivative, and g here is our Gaussian. So as we said before, because of the associative property of this this operation, besides smoothing and they are taking the derivative, we can apply the Gaussian with its derivative. That's what is shown here. And here -1 and 1 is its generic derivative operator, and G is the Gaussian represented by a matrix. Here is the matrix. This is the G, and this is H, which is -1 1. This is the generic derivative operator, and this will result in a function of that is the first derivative of Gaussian. Like when we apply this derivative operator to this Gaussian function, it will result to this graph, and it's the derivative of Gaussian, and which when I apply it to the image gives me the derivative of Gaussian smooth image. So we do this in x direction, and then in y direction. Here we can see here this is the derivative of Gaussian in x direction, and we can see here the picture below, and this is in x direction, and this picture below, this is the picture of this plot, and here we can see the 0 values is represented by the gray pixels, and negative is represented by the black. We can see here the positive values. We can see here the values above the 0 is represented by the gray, and the values below the 0 or negative values are represented by the black. And it's same in y direction. We can see here it's the same in y direction. Now this is how we get the Gaussian and the smooth like the derivative of this Gaussian in 2D. Now the question arises, like how big the Gaussian should we use? We can see here, as we studied in our previous lectures, that we can pick a different size of Gaussian and we can get more or less smooth version of the image. And the same is true here when we compare to the derivative. So we can change the sigma, like we can see here, we can choose the size of Gaussian and get the smooth. Like when we use very small size of Gaussian, then it's not blurred that much. But if as we increase the size of Gaussian, the degree of blurring gets increased, and here we can see with the bigger size of Gaussian, the image is blurred strongly. And here as we change the size of Gaussian, it also affects the like the scale of feature that is detected, or the scale of edges that is detected. So we change the sigma, the size of Gaussian, and when we do it, we will get the enhancing the magnitudes of the derivatives as a function of how quickly the image varies over the space. So smaller the sigma, finer features are detected, and larger the sigma, large scale edges are detected. And as we can see here, the smaller values, the finer features are detected, and larger values, large scale edges are detected. And now we know how to compute the smooth derivatives and gradients. Now we can return to the question like how do we gradually find the edges, and fundamentally it's a multi-step process. Like first we do smoothing, like derivatives to suppress the noise and compute the gradient, and next we threshold to find the regions of significant gradient, and next we thin to get the localized edge pixels, and finally we link or connect these edge pixels. We can see here like we smooth and then we threshold and we get the localized edge information, and finally link or connect the edge pixels. So far we have discussed about the primary edge detection technique. Now we'll talk about the canny edge detector. Canny edge operator works in the following way. First, filter the image with the derivative of Gaussian, then find the magnitude and orientation of gradient. Next we do what we call the non-maximum suppression, which is the thinning that we will talk about a minute later. Then there is a linking operation where we're gonna detect we're gonna use two thresholds, low and high, and use the high threshold to start edge curves and the lower threshold to continue them. So to illustrate the canny edge detector, we start with the Lena image, and if we are to take just the magnitude and gradient, it looks like this. We can see here it's just the magnitude and magnitude of the gradient. It looks close to edges. It's somehow when we see it, it looks like edge, but it's just a gradient image. And next we can threshold that gradient image. Now we can see a bunch of stops going which has gone away, and the gradient which is not high enough is removed. We can see like here the edge looks more clearer than just only the gradient. Here lots of like details have been removed, and then we do operation called thinning. We can see here which we call non-maximum suppression, and in the thinning we can see like it's the thinnest version of the edge, and basically saying what we have got a bunch of points that exceeds the threshold locally, and we will pull it out that exceeds the most, and what we do is that it's just the thin version of this thin version of this thresholded edge. And the question arises why we need to do this thinning operation. Here let's look at this image, and this is the Lena image and the gradient image of this Lena image. And if we take just a small version, small part of this, small segment of this this image, we can see that there is a kind of thick part that exceeds the threshold. We can see now if we plot this as a 1D function, like it starts with the lower value and goes up, and when we take the first derivative of this profile, intensity profile, what we found is like the first derivative exceeds, like some part of the first derivative exceeds the threshold, and this value that exceeds this threshold gives us the thick edge. So we want to turn it into a thinner edge. So the way of non-maximal suppression, like the thinning is done in canny operator like this. We'll see here, like in non-maximal suppression we try to find edge points to find the edge points, we need to find the local maxima of the gradient magnitude, and broad ridges must be thinned so that only magnitudes at the point of greatest local change remain, and all the values along the direction of gradient that are not peak values of the ridge are suppressed. We can see here this is the set of intensity value, and we can see here the value we can see here the direction of edge. And what we do is we consider the magnitude, pixel magnitude on the direction of a gradient, and we compare these values with the edge pixel. And if the magnitude, like let's say that this is represented by pixel magnitude of ij, and if this magnitude ij is less than its nearby magnitude along the direction of gradient, and like there are two magnitudes, one is magnitude magnitude at I1J1 and another one is magnitude at I2J2. If this magnitude at Ij is less than magnitude of I1J1, or magnitude of Ij is less than magnitude of I2J2, then we will make this value to 0, or we will suppress this. Otherwise we will retain its value. So what happens is we get the thinned value. However, with the thinned image also it comes with some problem, like the pixels along the edge didn't survive the thresholding. We can see here that the edge got discontinued in this area, so it may also come with some problem. So what we have to do is we apply high threshold to detect the strong edge pixels and link those edge pixels to form the strong edges, and again we apply low threshold to find the weak edges, weak but plausible edge pixels, and extend the strong edge to follow the weak edge pixels. Let's see in more detail about this. Like this is the hysteresis thresholding or edge linking. As we have said before, that the output of non-maxima suppression still contains the local maxima created by the noise. So can we get rid of them just by using the single threshold? If we set the low threshold, some noisy maxima will be accepted too, and if we set high threshold, true maxima might be missed. The value of true maxima will fluctuate above and below the threshold, and that will result in fragmenting the edge. So a more effective scheme is to use two thresholds, a low threshold TL and a high threshold TH, and it's usually usually TH is set as a double of TL. So we can see here, we check the maximum value of gradient value is sufficiently large or dropouts, so we use hysteresis, use the high threshold to start edge curves and low threshold to continue them. And here is the example of hysteresis thresholding. We have got the original image, and with high threshold and with low threshold and hysteresis threshold, we can see here in high threshold there are lots of discontinuities of edges, and in low threshold it consists of lots of unnecessary details which may be created by noise or some other source. And with the hysteresis threshold we get just like the required details of the image. We can see like there is no more discontinuity in edges, as well as unnecessary details are not included in this hysteresis thresholded image. Okay, now let's talk about again the edge detection using the second derivative. What we have studied, as like we have discussed earlier about the one-dimensional case of second derivative of Gaussian. So we have here is our original Gaussian. Here is the original Gaussian, and when we applied the second derivative of this Gaussian, will look like this. It is second derivative Gaussian, which is the Mexican hat operator, and which is the it is the inverted Mexican hat operator. And when we applied that to f, this function, it's same thing as taking the second derivative of the smooth version. So we were looking for the zero crossing on the bottom of the graph, and that corresponds to where the edges are. This is the zero crossing, and this will give us about the this will tell us about where the edge is located, and it's in 1D. Now when we talk about this in 2D, we have got the 2D function here, and here g x and y gives x and y direction, and sigma gives the standard deviation, and here we have got the Laplacian operator, which is the second order, this is the second order differential equation. And if we combine these two, this Gaussian and the Laplacian operator, we get this expression, and it results in the, when we plot this, we will get a Mexican hat operator, and it looks like this. This is our Mexican hat operator, and when we apply this in this original image with the Laplacian of Gaussian, we get the standard deviation of 1. With the standard deviation of 1, we will get this image as a result of applying Laplacian of Gaussian.